Okay, we're getting there, and by there I mean towards the end of this unit of study 3.2 on DC circuits, and here's another example of RC circuit. Now, in the diagram shown, there's only resistors, but just wait. On the second page, you see it's a combination of resistors and capacitors. So, let's start from the start. Now, this says it represents a circuit that a group of physics students are analyzing. The power supply is variable, so it can be changed from 0 volts to 2 volts to 4 volts to 6. In fact, we see this data table, and that's exactly the case. The voltage has been increased and represents our independent variable going from 2 volts to 4 to 6, and as the voltage goes up, then the amount of current read in this ammeter also goes up. And it seems to be somewhat in accordance with Ohm's law, at the very least, as the voltage is increased from 2 to 4 to 6, the current flowing in the circuit increases from 40 milliamps to 55 to 97 and so on. Now, if you try to apply Ohm's law and say R is equal to V over I, and you take any of the data in a column, you're not going to get consistent values for the resistance because the data table shown here actually includes the type of errors you might get anytime you make a measurement, right? So I say you never have and never will make a perfect measurement. Measurements are always subject to inherent error. So the best approach would be to make a graph of voltage compared to current. Now, even though it looks like the voltage represents the independent variable, as we can see it was arbitrarily increased in even increments, it's typical to put the independent variable along the x-axis, but the theory is governed by Ohm's law that says V equals IR, which can be re-expressed as V equals R times I plus 0. And then it's in the form y equals mx plus b. So it's probably more reasonable to put voltage on the y-axis, current on the x-axis, and therefore the slope of the graph will give us the value of resistance. So instead of using the values of voltage and current given in any column of the data table as a way to calculate the resistance, let's make a line of best fit to this data. So you can see that I've put voltage on the y-axis. I've color-coded this, right? Voltage here in red. Anyway, all the data points have been plotted already. So for example, this data point of 2 volts and 40 milliamps is here, and this data point of 4 volts and 55 milliamps is here. I know that 0, 0 corresponds to the theory expressed by Ohm's law, right? With 0 volts, we would get 0 current. So I would expect my line of best fit to intersect the origin. So let me try to draw in the best line. Now, fortunately, my note-taking app automatically makes straight lines, and all I have to do is adjust it. Well, no, that's probably too low. So that's probably pretty good right there, yeah? I don't need to extend it this far. So now I can pick any 2 points along the line of best fit in order to calculate the slope, and I think I definitely like the origin as one of the points, and then another point that's far away from there. I like this point a lot, because if I read across my axes, there's 12, of course there's 200, so slope being rise over run, the resistance then is the slope of this graph, 12 volts divided by 200 milliamps, or in other words, 12 volts divided by 0.2 amps, 120 volts divided by 2 amps, however you want to say it. It seems like the resistance is 60 ohms. Now, what resistance does that represent? That represents the overall equivalent resistance of this whole circuit, which is this value R number 1, which is unknown, and then I can say that R2 and R3 are connected in series, right? They're just along one single branch of this circuit. So let's just say that that effectively is 100 ohms, right? So 2 resistors connected in parallel have an equivalent resistance of 60 ohms. And anyway, now the line of best fit has been made. We've answered part A. Part B is calculate the total resistance of the whole circuit. That's the 60 ohms we found. But now we've got to figure out what's the value of just this R number 1. So resistors in parallel, right? We got 1 over 60 is equal to 1 over R1 plus 1 over 100. That means 1 over R1 is 1 over 60 minus 1 over 100. Yes, that means R1 is equal to 60 times 100 divided by 100 minus 60, which is 6,000 divided by 40, which is 600 divided by 4, 150. Looks like R1 is about 150 ohms. Ooh, I hope I'm not coming at you too fast with that one. If you need to pause and rewind or calculate it yourself, feel free to pause this video at any time and grab a calculator and double check the work. They tell us that this variable power supply is fixed at a value of 12 volts. Oh, how convenient. I happen to have chosen 12 volts. So we already know at that given value, the current would be 200 milliamps or 0.2 amps. So what's the amount of current through R number 2? Let's see. Clean this up a little bit. We can do some erasing. What's the value of the current through R number 2? This is 12 volts. Junction A. Junction B, the electric potential at A is 12 volts. The electric potential at B is 0 volts. So whether we're considering the path through the two 50 ohm resistors or the path through the 150 ohm resistor, the potential difference is 12 volts. So Ohm's law applies in total, and it applies in individual parts, meaning I can just consider this branch here highlighted in orange as a path along which Ohm's law must apply, meaning the current along that path has to be equal to the potential difference across that path divided by the resistance of that path, which in this case is 100 ohms. So even though they're saying what's the current through the 50 ohm resistor, I'm not going to plug in 50 ohms for the resistance. I'm not going to say I equals V over 50 because 50 is not the resistance on the full path for which I know the potential difference. See, I don't know what the electric potential is here. Well, actually I do. I know it's 6 volts because these two resistors are acting like a voltage divider with equal values of resistance, so it divides the voltage in half. Anyway, in general, I wouldn't know the value of that electric potential if these were two different value resistors. So what I'm using is the resistance on the whole path and the voltage across that whole path to find the one value of current through that path, right? So when we divide 12 volts by 100 ohms, how easy is this? We get 1.2 milliamps. So 2 milliamps is flowing into the junction at A, and 1.2 of those 2 milliamps flows through the 50 ohm resistor, the one called R2. So there we have it, 1.2 milliamps. Okay, now this is where it changes to a study of RC circuits. Resistor 3 is removed and replaced with what we see here, a 4 nanofarad capacitor. Let's make this look a little prettier. That capacitor is initially uncharged, and the power supply is still 12 volts. Calculate the current in R2 immediately after the switch is closed. Okay, so some current flows through the battery. It reaches this junction A. Remember what we say about the initial condition for an uncharged capacitor? Its capacitive reactance, or what we're calling its effective resistance, is initially equal to 0. So what we really can picture this circuit as, what if this part of the circuit was just bare wire? So now we've got a current that reaches a junction at point A, and it splits up Some of it goes across a path with 50 ohms, and this R1 is still the 150 ohms we solved for earlier. The electric potential at point A is 12 volts. The electric potential at point B is 0 volts. So now we have 12 volts divided by, well, if I want to find the current through R1, I would divide by 150. But I want to find the current through R2, so taking the potential difference across the path. So in orange, this is a path with a potential difference of 12 volts, and it's also a path with a resistance of 50 ohms. So if I divide 12 volts by 50 ohms, what do we get? I shouldn't need a calculator for this. We get 2.4 milliamps. Now, a long time after the switch is closed, meaning in the steady state, now we say this effective resistance is infinite, and whatever current is flowing into the junction at point A, well, now it no longer splits up. The current that flows through the battery and into junction A just all continues past the junction through resistor number 2, and current is only flowing in this loop on the left. This effectively becomes like a dead branch due to the fact that there's infinite resistance in the capacitor, or for the capacitor. So, will the magnitude of the current in R2 be greater than, less than, or equal to 2.4 milliamps in the steady state? It'll be less than, in fact, it'll be 0. Now the 4 nanofarad capacitor is replaced with an uncharged 10 nanofarad capacitor. Will the amount of current that we found immediately after the switch is closed in this previous question, part E, in other words, will this 2.4 milliamps still be the current, even when this is no longer 4, but rather 10 nanofarads in the initial condition, right? In the initial condition. So whether it's a 10 nanofarad or a 4 nanofarad, in the initial condition, its effective resistance is equal to 0, and so this still seems like a circuit initially at time t equals 0 that's made of a 12-volt power supply and then 2 resistors in parallel, one with 150 ohms and one of them with 50 ohms. And so the potential difference across the 50 ohm path is 12 volts. The resistance on that path is 50 ohms, and so the current would still be exactly the same or equal to 2.4 milliamps. Thanks for watching.